1. All righty. Well, welcome everyone. Hello and welcome to another broadcast of Meet the Scientist. We have Brian Campbell with us today, and I'll be introducing him in just a bit. I'm showing him to you now, but let's start here. I am Bonnie Murray, and I'm connecting from NASA Langley Research Center, which you see behind me, kind of an aerial view. NASA Langley is the mother center among the NASA centers. We are where the astronauts first trained. We have that facility here. The astronauts now train at Johnson, but the original Apollo astronauts, which we'll be celebrating with a 50th anniversary this year, those astronauts trained here at Langley. We were the first NASA center. There are now 10 NASA centers across the United States, and Brian Campbell is at Goddard Space Flight Center. So let him wave to you just a second. There's Brian at Goddard. All right. Thank you, Brian. We'll get back to you in just a second. So these sessions are called Meet the Scientist, and I already gave you a welcome. I'm going to welcome 2 classrooms in just a second. There are also people watching online, and we welcome you in as well. The sessions are part of a program run out of the University of Alaska Fairbanks called Arctic and Earth Signs. So if you want more information about these sessions and that program, honestly, best thing to do is Google Arctic and Earth Signs, and you'll get to their website and learn about them. That project is part of a collaborative of about 26 or 27 different projects that are funded through NASA Science Mission Directorate. So a big thank you to NASA Science Mission Directorate for the funding provided for the entire collaborative for Arctic and Earth Signs, and specifically, for these Meet the Scientist sessions. Today, we have 2 classes connected with us. So let's first go to Fairbanks, Alaska. And Miss Dybert, if you will unmute, I'll give your students a chance to say hello. You can go ahead and unmute for a second, and hello to students connecting from Fairbanks. Hi, welcome. So we have a 3rd grade class, is that correct? 3rd grade?
Yeah, yes, we're 3rd grade.
Awesome, and thank you. Hi, Ms. Diver. Good to have you in the picture as well for just a second. Hello.
We are,
go ahead.
We're having a little bit of a lag. We're hearing you twice.
Oh, has that been happening since the beginning?
Yes.
Oh, okay. I hear it. So somewhere there's another speaker is the only thing I can figure. Yes. I'm going to mute you for a second, and if you try and work on that, somewhere that you're getting feedback from a speaker in the room, and I apologize, we didn't fix that before we went live. I didn't realize that was happening. But see if you can fix that while I introduce the other class, and if not, we'll try something else. See if you can find another speaker, or turn off the speaker on your computer maybe, because you might have speakers coming out of the smart board. You know, I'm wondering if there's speakers on your computer and also speakers on the smart board, and one is feeding into the other. So let you experiment with that just a little bit, and I'll introduce the other class, okay? I'll be back. All right, so we also have a class in Metlakatla. Hello to students in Metlakatla.
Hello. I like Fortnite.
Hello, welcome. Tell me what grade you are. 5th grade class. And Miss Cecilyn, will you peek in and say hello for just a second there, please? There she is. Hello, Miss Cecilyn. Hi. And Miss Cecilyn's class is an after-school group, right? You usually meet after school, is that correct?
Yes, we do.
Yeah, so you're together during the school day today, which is a nice treat. I hope that's a fun time to be together. Awesome. Awesome time there. Okay, and your sound's okay? You're good?
Everything's
okay.
good.
Excellent. Let me go back and check on the sound in Fairbanks. All right, I'm talking again to see if you're hearing anything. Is the feedback gone? Okay, you're muted, so if you're telling me, I can't hear you. I see thumbs up, so that's good. Okay, your sound's okay.
Sounds way better. Okay.
Like we don't hear double anymore.
Excellent.
You
Okay.
don't hear two Bonnies.
Good. One Bonnie's wonderful. That's great, but that's enough. Okay, I'm so glad we got that fixed, and thank you for letting me know that was happening. So before we go any further, I want you, class, we're going to start with you, Fairbanks. Please tell Brian a little bit about where Fairbanks is and what the weather's like there today, okay?
Weather.
Tell your name.
My name is Eli, and I am 9 years old. The weather, it is, let's say, some days it's almost like a pattern. It's cold, then some days it's hot, but a lot of people have different opinions. Tonight, in my opinion, I think it's either just it was raining, but
We just had
it
recess.
stopped. We just had recess, but the rain, it stopped, and it was pretty warm in my opinion.
Especially for March, huh? Does it usually rain in March in Alaska, in Fairbanks, Alaska?
No, not really. Really cool.
Okay, who can tell the NASA scientist where Fairbanks is? Come up here. Say, my name is.
So my name is Anthony. We are basically in the very center of Alaska.
What's the land like?
It's
Flat.
flat, I would guess, but no, not really. It's cold all the time.
Okay.
Okay, thank you, Anthony. And so it's flat there. You're not living on the side of a mountain. It's pretty flat when you walk around. Is that true?
Yeah, but there's
Okay, but can you see mountains from there?
Yes. I can see them right now.
Okay, in particular, is there any big mountain you can tell me that you see?
Isaiah.
My name is Isaiah, and
All I see is just snow.
there's usually a hill right there, so we can barely see. But I see a big mountain behind the trees,
And it's Denali.
and it's Denali.
Right, thank you. I wanted to make sure I was getting it right. On a good day, when it's clear, you can see Denali from your location. All right, so we have an idea of where you are. Thank you very much. All right, let's go over to Metlakatla and get that information from them over there. Okay, Miss Cecilin, can you have someone tell us a little bit about Metlakatla?
Go ahead. What's your name?
My name's Sebastian, and we live in Metlakatla, Alaska. And
Where is it located?
it's located on the southeast of Alaska by Canada,
Show them the map. Where is it?
right there.
Okay, that's very helpful. By the way, if you're not, Brian, our scientist up there, if you're not used to that, making that symbol with your hand really helps you to see what's where. So yeah, Fairbanks is right about there, and Metlakatla is down here. Awesome, thank you very much. What's the weather like? Can somebody else tell me a little bit about the weather there today?
Level. Go ahead.
I'm Lowell, 10 years old, and it is sunny.
Speak a little bit louder, please.
You can come around here if you want.
That would be better. Come on up. I know you have to crawl out from between the people, but we can see and hear you better if you come on up.
My name is Lovell, and I'm 10 years old, and it is sunny in Metlakatla.
Okay, and the temperature, somebody else?
Mark Kelly.
The temperature in Metlakatla is 53.
Say it one more time.
53.
Degrees.
Okay. All right, pretty good. Okay, so Brian, we're going to come over to you. We're not going to get started with the presentation quite yet, but I want you to tell them a little bit about where you're connecting from and the weather and the land and that kind of bit.
So how's everybody? All right. So yeah, so I'm actually connecting from Greenbelt, Maryland on the East Coast of the United States. And I'm actually based though, so I should say I'm at NASA Goddard Space Flight Center, and that's in Greenbelt, Maryland on the East Coast of the United States. I'm actually based at Goddard Space Flight Center's Wallops Flight Facility, and that's in Wallops Island, Virginia, and it's just next to the Atlantic Ocean. So we're there because we launch a lot of rockets from where I'm based at NASA Wallops Flight Facility. So I'm at like the complete opposite part of the United States from where you guys are. And it's very cool talking to a student from Alaska, because last summer, my family and I took a trip to Alaska. We went to Juneau, we went to Sitka, and we went to Ketchikan. So it was very cool. We were on a cruise, so we didn't get to spend a lot of time there. I would have liked to spend more time there, but yeah, Alaska is a beautiful place, and I hope to explore more of it someday. So yeah, we're coming, live from the East Coast of the United States.
Yes, thank you, Brian. Yes, and so if you're familiar with the East Coast of the United States, there's a big chunk that's missing, if you will. It's flooded with water, and it's called the Chesapeake Bay. It's actually the site of a huge impact crater from long, long ago, and it has filled up with water. And the Chesapeake Bay is a feature that defines Goddard and Langley to some extent, because Brian at Goddard is at the top of the Chesapeake Bay, and I'm at NASA Langley, which is at the bottom of the Chesapeake Bay. So we sometimes joke and say that if we put a note in a bottle and let it go, Brian could send me a note down the Chesapeake Bay in that water.
And if it would come down the Chesapeake Bay and out to the ocean and then go a little north, then it would hit Wallops.
That's right, yeah.
Yeah.
And something Brian didn't tell you about Wallops is, he alluded to it, but I want to get this specific point. It's a spaceport, right, Brian?
Well, Wallops, yes. Wallops is a spaceport, so we have everything from rocketry. We send rockets from Wallops, and we send rockets to the space station. We take supplies and instruments up to the International Space Station for the astronauts. And we also, we send rockets into our atmosphere to look at different things in the clouds and in the sky. But we also send lots of aircraft in and out of Wallops all the time. And I'll talk a little bit about that later during the presentation.
Awesome, yes. And there was a mission that was launched to the moon as well, correct?
Yes, called Laddie.
Yes, that looked at the atmosphere of the moon.
Yeah.
So that's why we say Wallops. Let me switch back over to me. That's why we say Wallops is an actual spaceport. You think of Kennedy maybe as where things launch, but Wallops also has that capability. So Brian, we're delighted to have you with us coming from Wallops and today at Goddard. So let's get ourselves ready to hear from Brian about the ICESat-2 satellite and trees around the globe and all of that. So I see that you have your 4 square notes in front of you. So if you'll get those out, you saw Brian's name there, and it'll be back up on the screen again in just a moment. So make sure you put that onto your 4 square notes as the speaker that you're listening to. Brian is connecting from Goddard, as you heard, and he works with the ICESat-2 program. So you want to put ICESat, spell it however you think, and if you have to make corrections later, you'll get it. Another vocabulary word I want you to be looking for is photon. So let's take some guesses. How do you think photon is spelled? Any guesses from either school? Okay, I see Fairbanks has some guesses. If you want to unmute, thank you, Ms. Dybert. Go ahead.
James will tell you how to spell photon.
Okay, thank you.
Hi, my name is James, and I'm 9 years old. And photon is spelled F-H-O-T-O-N. P-H.
Awesome. Great. It's no problem to make a mistake. That's how we learn. In fact, I'll be honest, NASA has crashed more missions into Mars than we've landed successfully. Not really exciting, except that by crashing those missions into Mars and having mistakes, we learned what not to do, and that's important. So never worry about mistakes. Just get your learning from them and move on. So yes, it's P-H-O-T-O-N. Excellent. So you've got some words to look for as you listen to Brian. And Brian, I'm going to turn it over to you at this point. and let you start sharing. Let me make you the larger screen. There you go. And let you start sharing information with the students.
All right. All right.
Okay,
So
Brian,
we're going to,
Brian
yeah.
Campbell.
Ms. Divert, you're not muted. Sorry about that. It's probably my fault because I asked you to unmute. But if you could just, thank you so much.
All good.
All good.
All right. So, yeah, so I hope you're excited about learning a little bit about the ICESat 2 satellite. You might not have ever heard of it before, but it's a super important mission, especially for you in Alaska, because we're actually studying a major part, of Alaska as part of the mission. So the ICESat 2 satellite, that's the abbreviation for it. It's called an acronym. It's actually the Ice, Cloud, and Land Elevation Satellite 2. And the reason it's number 2 is because we had an original ICESat satellite that was in space from 2003 to 2009. And this is the follow-on mission called ICESat 2. So ICESat 2 was launched September 15th of 2018. So not too long ago, just about 6 months ago. And it uses an incredible system to take measurements. So we're going to get to that in a second. But what you're looking at here, this is a graph with lots of stuff on it. It's really confusing. But what you're looking at here are all the NASA Earth Science satellites that are in space now and will be launched up to the year 2023. So if you can see that, all the ones that are in blue, light blue, those have been there up in space for a long time taking measurements. The ones in green, now when I say a long time, I mean 3 years up to what are called extended observations, and that would be 10 years, 3 years to 10 years. The ones that are in green are ones that were recently launched over the last few years, and those are the ones that NASA is putting a lot of emphasis on right now in the measurements they're taking. And then the ones that you see in orange and yellow, those are ones that are being developed right now and will be launched in the future. Now, why I show this graph, why it's so important is if you look on here, ICESat is just one tiny satellite with all these other satellites, because we need all these satellites simply because all these satellites tell us something different about our planet. There's not one satellite in space that can tell us everything. So we think of all these satellites like a big jigsaw puzzle. Putting together a puzzle, you need all the pieces to understand what the puzzle is showing. So with these satellites at NASA, these Earth observing satellites, we launch them into space and they all measure different things, like things in the atmosphere, like clouds and precipitation, looking at snow, looking at ice, looking at carbon. We look at vegetation and trees. So all these satellites look at different things, and all of them are pieces to a puzzle that help us understand our planet and our entire planets and the many ecosystems on our planet. So I'm showing you that because there's lots of moving parts literally in space right now looking at our planet. And this is just showing you all the pieces of this jigsaw puzzle that we have now and then we're going to have to help us even better understand. And I say to help us better understand in the future because some of these satellites that haven't been built yet, our technology is advancing so quickly on Earth that the technology that we have now on ICESat 2, when a satellite is launched 10 years from now, that technology is going to be far more advanced than what we have right now. ICESat 1 was super advanced when it was built in 2002. Now it's called a dinosaur in technology because the stuff that they use, they don't use it anymore because it's not as efficient as what's in space right now with ICESat 2. So the ICESat 2 satellite, here's what it looks like. This is an artist's concept of it because there's nobody floating in space with a camera taking a picture of a satellite like this. So what you're seeing here is you're looking at the satellite. The main instrumentation is inside that big silver part on the left side. That's where all the fancy equipment is, and that's where the power supply is. And then you see that arm or that wing. Those are the solar panels. So those solar panels are super cool because they're the ones that actually keeps the satellite working. Solar panels take in the sun's energy, converts it to power for the satellite. But what you see coming out of the satellite here, you see these green lines. These are the word that you spelled earlier. These are trillions and trillions of photons. They're from a laser. You've all seen lasers, I'm sure. There's lots of lasers. You've seen a red laser and maybe a green laser, and there's purple and blue lasers. But what this satellite does is this satellite sends a laser pulse. It leaves the satellite and it bounces off the Earth's surface, and then it comes back to the satellite again. And what happens here is over time, we can determine what the height is of things on our planet, how tall things are, not people, but when you're thinking about it, you're looking at areas like mountains and clouds and bodies of water and buildings and trees. That's a real important one for today. And ice, super important for Alaska and Greenland and Antarctica. It's looking at how the ice is growing and shrinking over time. And we're seeing that accelerating over time really quickly. So we have a satellite in space that's able to help us understand how fast the ice may be melting in the Arctic and Antarctic and, around Alaska. So, we're doing that right now. The satellite's been up for 6 months. We're going to release the data most likely next month for the public. So, we'll get a good idea of what the satellite's been seeing over the last 6 months. So here's a short video here showing you exactly what the satellite's doing what the satellite did once it got launched into space. So all these things have to open, and there are scientists and engineers on the ground when this is happening to make sure all this is working right. That door that you just opened was probably the most important part of the satellite. And that was one guy here at Goddard. That was his job, to design a door that could open in zero gravity. And why that's so important is you saw the door open and then the lasers were able to fire. If the door didn't open, we'd never be able to get a measurement. So, one guy had this, probably the most vital job, I think, to get this satellite working. If that door doesn't open, we don't get measurements. So super cool how the scientists, super smart scientists and engineers were able to do that. So this is showing you the satellite as it's moving through space. And this is what it ends up looking like once everything is open and functioning. So I mentioned a little bit about what the satellite does. It measures the elevation of our planet. I'm going to show you a video now, which is super cool. It's called ICESat Elevates Our World. And what you're going to see is you're going to see these different green dots all over the planet. You won't be able to see this if the satellite is overhead. This is just what an artist was showing you, how the satellite will be measuring things. So I should mention that you often hear, don't look at laser beams directly because you cause blindness, which is true. But this satellite is approximately 400 miles above the Earth, and it's moving around the Earth very quickly, over 15,000 miles an hour. So even though it's a laser pointer and you look up when it's overhead, nothing's going to happen. I like to explain it this way. Imagine if somebody stands and holds a flashlight you're standing right in front of them, they hold a flashlight in front of your face, okay? That's going to be very bright. But if they walk 400 miles away from you and turn on that flashlight and shine it towards your direction, you're not even going to see it, okay? That's the way I like to explain it, because people do get scared when you talk about lasers, and, we have nothing to worry about. It's been up there for 6 months, no reports of anything, so we're good to go. So the satellite's taking some awesome measurements. So let me show you this video here, and we'll talk about it a little bit. But this is called ICESat Elevates Our World.
From satellite data, we have a very good handle of how our Earth looks like. We can see oceans, we can see the sea ice, we can see our forest. What is much, much harder to measure is how high things are on a global scale. Almost impossible.
ICESat adds the third dimension, the elevation. Repeating measurements from ICESat will allow us to measure changes in the ice sheets or in the ocean or in land.
ICESat is designed to measure the changes that are going on in the cryosphere, in the polar regions.
All the change is at the edges. Those are the steeply sloping parts of the glacier that interact with the ocean, and that's where all the action is. That's where all the mass is being lost.
In order to estimate the mass changes, we need to know the height of things. The mission ICESat carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System.
ATLAS sends out small pulses of laser light 10,000 times a second. And by measuring precisely how long it takes that light to go from the spacecraft down to the Earth and back up to the spacecraft, allows us to figure out what the height of the surface is beneath ICESat 2.
We need to measure the time of flight of a single photon or a single laser pulse with a precision of a billionth of a second.
NASA engineers had to come up with entirely new ways of measuring time very precisely.
A billionth of a second translates to an elevation change precision of just a few centimeters. Climate change is amplified in the polar regions. ICESat 2 is designed to measure those areas and will help us to understand what's going on with our planet.
All right, so yeah, that video is pretty cool because it shows you a lot about what the satellite's doing. Satellite is super cool because it can measure so precisely, and what it does is the satellite, those laser pulses you see, those photons, each laser pulse contains about 300 trillion photons. Photons are the little particles of light that make up a laser pulse. But this satellite, the technology is so advanced is that it fires off or sends out 10,000 of those laser pulses per second. Okay, so I have a question. I'll start with Fairbanks. I have a question for you guys. I'm not going to give you any other information about this, but the satellite, as I mentioned, sends off every laser pulse is 300 trillion photons. Now remember, laser is light, right? So light gets scattered, gets absorbed, gets reflected, refracted. So we're not going to get all those laser photons to bounce off the surface and come back to the satellite because there's lots of things that could cause them to be destroyed. How many out of 300 trillion do you think we actually get back to the satellite? I'll start with Fairbanks if you want to unmute and see if we can get any good answers.
About 5.
We guessed 5.
10, maybe?
10?
5 or 10? Are you saying 5 or 10 out of 300 trillion?
I'm guessing 20.
Out of 312 trillion. They're guessing 5 or 10.
5 or 10, okay.
21?
Is that too low?
No, we'll keep it there, and I'll give you an answer in a second, and then we'll go to Metlakatla. We'll see what they think.
Go ahead, Robert. Tell them what you said.
10 billion.
Wow. Okay, so we have one school that's very very low, and then the one school that's thinking very high. All right.
Any other guesses from Metlakatla?
Yep. 21 trillion.
Let's take 2 more, Miss Esslin.
Michael.
1 million. 200.
Michael.
Okay, I heard 1 million and I heard 200. Okay.
That's me. 1,500.
1,500. All right, so you're going to have to think about your answers for a second because I want to talk about one other thing. Stay unmuted, please, because I want to ask another question, then we'll go back to Fairbanks. So, since this is called the ICESat 2 mission, our main focus is ice. So, when we look at ice, okay, we know that ice is cold, right?
Yeah.
Right. So, but how, if I tell you that ice keeps our planet cool, how does it do that?
And we're over to you, Metlakatla.
Yes.
Go ahead, give your answer.
Like it helps like cool the water down for us.
Okay, so you're saying that the ice that's already in the water, like an iceberg or sea ice or something, keeps the water cool, kind of like an ice cube does in a glass of water?
Yeah.
Okay. Anybody else in Metlakatla?
Lily? Does anybody else want to make a guess? Kelly, go ahead.
What was the question?
How does ice keep the earth cool?
Since it keeps water cool and since water's all around the earth, I think that it keeps the ocean cool down, which keeps the earth cool down.
Okay, so it keeps the ocean cool, so therefore the rest of the earth stays cool.
Yeah.
Right? Okay. All right, let's go over to, if you could mute Metlakatla, and then we'll go over to Fairbanks and check with them, see what they think. How does ice keep the earth cool?
It freezes.
It freezes and it spreads over the earth, I'm pretty sure.
Okay. All right. Anybody else?
It goes everywhere in the city.
And Kira.
Like, so the ice freezes on the water and it goes into the bottom.
Ice. You hear that?
Can you repeat that, please?
Yeah.
The ice freezes and it doesn't go to the bottom.
Oh, so it freezes and it floats on the top?
Yeah.
Okay. Okay. All right. So how about I tell you, okay, that's good. Thank you for the guesses, the educated guesses, I should say. Yeah, so the ice can act like ice cubes, okay? But what happens here is that ice and snow, I'll say, is usually white, right? White has something called, now this is a big term, it's called albedo. I don't want to get much into albedo. It's spelled A-L-B-E-D-O. But what that means is albedo means how reflective a surface is. So for instance, like your white walls in your classrooms, that reflects a lot of light. If your walls were black or brown or gray, it wouldn't reflect a lot of light. But since they're white, they do. That's why they paint them white, so you have a nice, bright classroom. So what ice does, ice has a high reflectivity. So we have something in the sky called the sun, okay? The sun sends down a lot of energy all the time. And what happens is that sun's energy hits that ice and snow, and it gets reflected back off into space. When the ice isn't there, like when the ice is melted, when the ice isn't there, that sun's energy can't be reflected and it gets absorbed by the land or the oceans. So the planet is actually kept cool when there's more ice because more of the sun's energy is being reflected back into outer space. And when there's less ice, the warmer the planet. When there's more ice, the cooler the planet. And that doesn't have anything to do with weather. That's just a climate thing. So over time, when we start losing lots of ice, our planet's going to be warmer. It's going to get gradually warmer. So yeah, that's how it keeps it cool. And I have a quick graphic here. It shows you exactly what I'm talking about. There it's bouncing off the ice, but when the ice and things disappear, you can see a lot of it gets absorbed. Less of it gets reflected back into space. So it gets absorbed by the land and by the water.
And there's that word albedo, if you wanted to put that in 4 square notes. Thanks, Brian.
Yeah, that's a fancy scientific word, so you'll be ahead of all your, you can ask your parents that, your parents or your grandparents or anybody in your family if they actually know what the word albedo means. It's not a word it's not a common word outside of, the scientific world. So you have one up on everybody else. So yeah, super cool. Now, when we talk about studying ice with ICESat 2, I like to talk about the Earth's poles quickly because sometimes there's confusion between them. Now, if you look on the left side, we have the North Pole. That's called the Arctic, okay? You guys are up in that area, up around the Arctic. So if we look at this, the Arctic, in the center of where the North Pole is, that is frozen, and that is called Arctic sea ice. So that is frozen salt water. That is frozen ocean water. There's no land right there at the North Pole. It's frozen water. And that's called Arctic sea ice. But then next to it, right there, in the Arctic, we have Greenland, which is an ice sheet. So it is frozen ice and snow on land. And then I have a polar bear there because polar bears in nature are only found at the North Pole. Okay? They're not at the South Pole, just the North Pole. If we look on the other side of this image, we have the South Pole where penguins live. Okay? They don't meet in nature. Okay? The only time they might meet close by is in a zoo somewhere, but they don't meet in nature. They're a huge distance away from one another. But the South Pole is kind of opposite because in the center there's Antarctica at the South Pole. And Antarctica is like Greenland. It's an ice sheet, so it's land covered with snow and ice. but surrounding it is called the Antarctic sea ice. So around it is frozen seawater or salt water or ocean water, okay? So it's kind of opposite. The Arctic is a little bit different, is different than the Antarctic. You have sea ice in the Arctic surrounded by an ice sheet, and then we have in the South Pole, we have the Antarctic ice sheet surrounded by the Antarctic sea ice. And that's good, just a good differentiation to know. You know, if anybody says, oh, they saw a movie of polar bears at the South Pole, well, you can say, nope, you probably saw it was the North Pole. You know, so, and there's lots of things about penguins out there. I mean, there's penguins other places. You know, there's ones in, I believe, South America. I think there's some in Australia or New Zealand. There's different, I think even South Africa, there's penguins. So, but no polar bears at the South Pole. So when we talk about the ice that we're measuring, this is a cool graphic. I'm going to play this while I'm talking. And this is called Arctic sea ice maximum. So what you see here, you're going to see the changing ice in the Arctic, and it's going to come over towards Alaska in a second. But what you're seeing is you're seeing the beginning of, well, actually, you'll see the date here. It started in September, so it's heading towards winter in the northern hemisphere. And as you can see, it's getting colder and colder, and more sea ice is freezing. And you can see the date here. We're in January. It's going to go all the way up to basically last week. And as we're going in, you can see we're moving over towards Alaska. You'll be able to see as the springtime is about to hit, you'll see less and less sea ice. You'll see the sea ice kind of pulling away from Alaska. And you can see it right here. Let me back it up right here. You can see it kind of pulling away, actually right there. You see it pulling away a little bit. So that's where the melting is taking effect. Now, the sea ice maximum, what that means is that is basically the maximum means that's the most ice in that area for the winter season. So that's what basically the ice reached its maximum extent, you know, so it pushed away from the North Pole and moved out, okay, and its extent. In the summertime, it hits what's called an Arctic sea ice minimum, so the temperature is going to be warmer, so there's going to be less sea ice. But what we've been seeing over time is that the sea ice minimum and the maximum are getting less. It's getting less and less every year. And that's one of the things we're looking at with ICESat 2 is we're trying to fine tune that detail to where exactly, you know, we see the most ice loss. You know, is it in Alaska? Is it around Greenland? Is it at, you know, at the North Pole? That's why we have the satellite in space. So back to your question that I asked you about the numbers, 300 trillion, okay? Each laser pulse fired down is about 300 trillion photons. I want you to listen closely to this video. You'll hear what the number is. I'm going to tell you one of the schools, I won't tell you which one, but one of the schools was almost perfect in guessing. So let me go to it.
300 trillion. That's about how many photons in each laser pulse fired by the Atlas instrument. It sounds like a lot, but as the photons sail through the atmosphere and bounce off the Earth, they reflect back, just like any light, in all directions. Atlas receives only the photons that reflect straight back to the instrument, just about a dozen photons. That window of photons received must be very small in order to keep the timing error of those photons very small, which allows scientists to calculate elevation very precisely.
Pretty good. All right, so did you hear the answer? The answer was 12. So which school was closer? All right. Is that Fairbanks? All right, so very cool. So good guesses. They're good guesses on both ends because, you know, you had no idea. It was a tough question. I gave you no point of reference for it, and 300 trillion is a really big number. But it doesn't sound like a lot. But if you figure every second the satellite sends off 10,000 laser pulses, and at every one of those 10,000 laser pulses, we get 12 photons back to the satellite. That's over 100,000 points of data from the satellite every second. So it's a lot of data coming back from the satellite, you know, in a short amount of time. So that's why we're able to get, we're actually getting about 1 terabyte of data back per day from the satellite. So there's a lot of data to look through, and but it's really high-tech data that helps us understand what's happening in our polar regions and around the world. I should mention it also, of course, goes all over the planet. It's not just the polar areas, because remember, it measures along with the ice, It measures trees and buildings and ocean surface height and mountains. So anything with elevation, it's able to measure. So we'll play this one. I'll talk through this one when I'm on here while this is playing. But yeah, so this is cool. This is showing you the actual launch of the satellite. I was there for the launch. It was at 6:02 a.m. Pacific time on September 25th from Vandenberg Air Force Base in California. And you'll see here, this is just some of the information. These are some of the first points of data that come back. They don't look like much, but all those little thick blue lines are all the trillions of photons that have come back over time. So we're able to look at cracks in the ice. We're able to look at anything that is very small in detail. This satellite can see changes in the ice as small as 2 centimeters. Okay, 2 centimeters is a super small number, but if the ice melts just 2 centimeters, the satellite will be able to detect that because the technology is so fine. So yeah, ICESat-2 satellite uses an onboard laser. I said laser altimeter. I didn't even mention that word yet. Sorry, I didn't mention altimeter yet. That's just the name of an instrument that measures the height of something. It's called an altimeter. Okay, that's just the fancy instrument name, the scientific name for it. But it uses a laser altimeter system. So basically, it's an altimeter that uses a laser to send these photons back down to the Earth and then back to the satellite, and then it collects that information about how long it took to go back and forth from the satellite to the Earth and back again. So one thing I'm focusing on here, you'll see on this image, you'll see trees, and these trees look like they're glowing green. That's just showing you what the lasers, you know, that's showing that the lasers bounce off trees. Okay, they don't look like that. It would be kind of cool to see trees looking like that in the real world, but it actually doesn't look like that, which is unfortunate. But you know, it would be exciting and kind of scary at the same time. But we have something called the Trees Around the Globe Student Research Campaign, which you'll may be able to become part of either now or in the future. You know, it's going to be on for 3 years. We're about 3/4 of the way through our first year, and there's a couple more years after this. But what this does is this satellite allows students to go outside and take tree height measurements simply by using a handheld instrument. And you can take tree height measurements and then collect that data and then look up the ICESat-2 satellite data and then compare your data to the satellite. What's super cool about that is that NASA scientists we want your data. We want to be able to look at your data so we can compare it to the satellite and say, hey, does the data that the students are collecting, does that data match up with our satellite data? And if it does, oh man, we have lots of good data that we can use for research, you know, and help us understand what's happening, you know, in our ecosystem. And this campaign is through the GLOBE program. It's a Global Learning and Observations to Benefit the Environment. And it's a international program of students, teachers, citizen scientists, and the general public who go out and take measurements in their local environment to help us understand our planet just a little bit better. And this campaign is part of this. Is a student research campaign because it's focusing on students taking data, looking at tree heights, and then once the ICESat-2 data is available, comparing their data to the ICESat-2 data, and then designing research projects using this data. And they can be simple research projects, you know, like how tall is that tree and, you know, outside of my school or in my backyard, or let's map out the every tree in a forest. Okay, it can be that simple or that complex, you know. And this is all part of the campaign. We have students all around the world. I should mention the GLOBE campaign. Sorry, the GLOBE program is active in 121 countries now. So we have students from 121 countries participating. And if you want to interact with students from around the world, you know, join the GLOBE program if you haven't already, because the GLOBE program lets students talk to one another all the time about their measurements. For instance, I'm actually this Friday going to be working with some students in Ghana. You know, I'm going to do a live feed in Ghana, Africa. And we have students who are doing research projects between the United States and Croatia and Poland. So the Poland, Croatia are in Europe, and of course, United States. And then they're actually taking the same measurements at the same time period, and then comparing that information and creating research projects that are collaborations between these schools from different parts of the world. That's why the GLOBE program is so cool. And that's what the Trees Around the Globe Student Research Campaign does. We bring students and teachers together from all over the world by looking at trees and understanding how they make a difference in our environment. Tree height is super cool because tree height helps us do a bunch of things. Tree height is basically probably the most important way that we can determine if an ecosystem can grow trees. And then when we look at tree height also, tree height helps us with understanding what's called biomass. It's BIOMASS. Biomass is basically the total amount of organisms in a particular area. Like what is the biomass of a forest? What that's saying is that what are the total number of organisms in that forest, from trees to animals and everything. But if we look at just the trees and the biomass, we have to figure out how many trees are in that environment. So it's pretty cool. It's a great campaign. So hopefully you can do that sometime in the future or now. So this is just showing you some students who are measuring the screen chain slides. Yeah. So this is a student share time. We had some student share time with some of the tree height measurements. This one's over in Michigan, and this one on the right actually happens to be at Goddard Space Flight Center. Last summer, we had some educators out doing it. So they're taking measurements, looking at tree height using just a simple instrument. It's actually called a clinometer. It's super big word, but you can do it easily by just on the ground looking at a tree. So the campaign, this is a long URL for the campaign. Unfortunately, I don't have control over that, but it's a very long URL. And then I have some guidelines on here that I always mention whenever I mention the campaign. When you measure trees, they should be at least 5 meters or 16.4 foot tall, because in the scientific world, anything smaller than that is considered a shrub or like a bush. So anything this tall or higher is considered a tree. And then in order to do the best comparisons between the satellite data and your data, you can look for isolated trees or look for really tall trees that are in a grouping. They'll be easier to measure. Because if you have a lot of trees that are the same height, they're kind of hard to do, kind of hard to measure. So what I'm super excited to mention is that tomorrow we're actually releasing the new citizen science tool for measuring tree height. There's something called the NASA Globe Observer. And that is a citizen science program that you can do on just your phone or your mobile device to measure things in your environment. We started off with clouds, and then we went to mosquitoes, and then land cover, and then tomorrow we're releasing trees. So you'll be able to measure the height of trees by just using your phone. So we have a built-in clinometer on the phone, on the app, that you're able to simply, take a picture of a tree, and then you'll get the height of it doing a couple other measurements and movements with your phone. So we've been doing lots of testing. We actually have a Facebook Live event tomorrow. I don't have this on the slide because I just got the specific time recently. But the Facebook Live event is actually at 3:00 p.m. Eastern time. So I think they're 4 hours ahead of us. Are they 4 hours? So yeah, so that would be 11 a.m. Alaska time, for you to, if you want to check that out. And you just go to the NASA Earth Facebook page. Just look up NASA Earth, and you'll find a link there, and it'll be live from the NASA Earth website. Sorry, the Facebook page. So yeah, you can check that out. But you'll be able to easily, once this gets going, you'll be easily to take tree height measurements quickly. I'm one of the, I'm basically the tree science lead for this project, and I can go out now. I have a little advantage. I've been doing it for a while, but it's easy. Once you get to do it, you can go out and take a tree height measurement in probably about a minute. So it's super fast, once you get used to it. So it's very easy to do. Now, one of the last slides that I'm going to show you here is something super cool. It's called the Photon in Photon Jump. And remember I said that when the photons leave the satellite, they have to bounce off the Earth's surface and come back to the satellite again in order for us to get a measurement. So we created an animation called the Photon. Actually, it's called Photon Jump, starring the Photon. And I want to show this to you because it's super fun, because it gives a different perspective of what a photon has to do in order to fulfill its requirement. It has to leave that satellite, bounce off the Earth's surface, and get back to that satellite again if we want to use the measurement. So, all right, let me start this and enjoy the sound. It's super cool.
Attention photons. Prepare to measure Earth's changing ice. Laser pulse going to a photo. Departs in 5, 4, 1. Turn. Run. Excellent job, Phil. Your travel time has been recorded. Let's add it to the elevation data set. Ready the next group?
All right, so yeah, that's just a fun little video showing you, what a photon has to go through in order to get there. And we took of what are called a lot of scientific liberties with it because, we actually had people say, photons don't make noise like that. And I said, well, they don't actually have voices either, and they don't swim in space. So it's a cartoon. Okay, I basically said it's a cartoon. Deal with it. It's fun. It's bringing a different audience in. So I hope you guys enjoyed that video. So here I have a bunch of resources on the screen. This is showing you different websites. We have everything. We have something called the ICESat 2 Fun Zone. There's lots of cool activities that you can check out. You can actually, there's an activity using a ruler to measure an ice cube and try to get it measured basically before it melts. So yeah, it's pretty cool to do. And then I have a couple things on here. Oh, I should also mention, and I know, I believe Bonnie's going to mention this. I forgot to mention in the one point, despite us talking about it, but Operation Ice Bridge. So Operation Ice Bridge is it's something here that I have listed in the resources. Now, remember I said we had a satellite called ICESat, and that went from 2003 to 2009. And then we had one, ICESat 2, which launched in 2018. Well, that means we didn't have any data coming in on ice between 2009 and 2018. And what we needed to do is we needed to have a mission of some type that would bridge the gap of basically ice data in that time period. And that's called Operation Ice Bridge. And what we did is we put the same type of instrument, laser altimeters, on aircraft. And these planes with a crew and scientists and engineers on board each year flew over Greenland, Alaska, and Antarctica, measuring changes in the ice. So they go back every year and fly over the same areas and see the changes that are happening over time over the last year. And this has been happening since ICESat 1 stopped working and ICESat 2 started working in 2018. But Ice Bridge has about another year or so to go. So we want to continue the success of that mission because we didn't want a gap in that data to see what was happening. So then we can, like I said earlier, we can take pieces of that jigsaw puzzle. ICESat 1 was one piece of the jigsaw puzzle. Ice Bridge, Operation Ice Bridge was another, and then ICESat 2 was another one. Put all those pieces together, and we have a nice, complete data set from all the way back in 2003 to the present day of what's happening in the ice over Greenland, Alaska, and Antarctica. So, take a look at that. You Google Operation Ice Bridge, and there's lots of amazing imagery that comes up from these places that the scientists and engineers have taken from the aircraft. And a lot of those missions are the Operation Ice Bridge. Those people who work on that are down where I am. They're basically in my lab that I work in at NASA Wallops. And I work in the hangar where the aircraft are actually repaired and tested and everything. So quite often it's hard to get a lot of work done in my office, especially if a big aircraft is sitting outside my window and they're testing the engines. So it's really hard to hear. So I have to go into an internal office. But you know, it's science. It's all in the pursuit of science. So it's very exciting. So here's my contact information. I'll just put that up on the screen for your purpose. And you know, if the teacher wants to contact me about anything, that's fine. And Bonnie knows where to get me. So yeah, so that is it. I hope you learned a little bit of ICESat 2, and happy to discuss some more with you now.
Yes, thank you, Brian. Thank you very much. And thank you for sharing your contact information also and all of those links. And what I will do, there will be a recording of this session available. It'll be posted on the Arctic and Earth Science website. And it'll also be available on YouTube. And I will add all of those links to the YouTube location. So you'll be able to see those, and we'll get those out to you as well. So let's go to the classes and see what questions they have. And I also want them to tell you a little bit about the globe research that they're doing. So let's start with questions. Let's start with Metlakatla. And let us know some questions you have for Brian based on the presentation he gave, or questions about anything else you have about NASA and science and space. And then after a couple of questions, Ms. Cecilin, I'll ask the class to tell Brian what they're doing with their globe research, okay? So you call on students would probably work best, Ms. Cecilin.
So you guys raise your hand if you have a question. Kelly.
How long has Brian?
Big Michael.
Can you come up to the front, please? Because it's hard to hear in the back. Thank you.
How long were you doing your job?
So this is my 18th year at NASA. So, and I've been working with the ICESat 2 mission for 10 years, so the entire length of the mission. So yeah, I was actually based out here at NASA Goddard for about 11 years, and then I got married and then transferred to NASA Wallops Flight Facility. So about 18 years. And right before that, I taught high school for 4 years. I was a high school Earth and Space and Science and Physics teacher in Maryland.
Okay, does anybody else have a question?
Thank you for your question.
Morgan. Yeah, right there's fine. You can scoot back and stand up.
Hello, Morgan.
How do you work the satellites?
Oh, that's a good question. How do you work the satellites? So we have mission control on the ground, and the mission control for ICESat 2 is here at NASA Goddard Space Flight Center, because NASA Goddard Space Flight Center built the satellite. So it was all built here in-house. So yeah, we have mission control here. So that's how we work it. Now, if there's a problem with it, we have people ready to, you know, step in and figure it out. There's engineers always ready to, if there's a problem, you know, step in and figure out what's going on. But yeah, we work it here at mission control at NASA Goddard.
Okay. Sebastian?
Do photons go through? Could photons go through clouds?
That's a good question. Yeah, if the clouds are very thin, they can, like cirrus cloud, they can go through. But if the clouds are very thick, and this is this is like a cool phenomenon. With the original ICESat satellite, there were some people who were out in the desert in New Mexico, and there were really thick clouds in the sky, and they happened to have a camera, and they were filming basically from sunset to sunrise using basically a time-lapse camera. And what they did is, in one of the frames, they actually captured the laser photons hitting the clouds and bouncing around all the water droplets in the cloud. So the cloud was completely green. So yeah, so great question. If the clouds are really thick, the satellite's going to have a really hard time sending the laser pulses through the clouds. But if they're very thin, it can penetrate that. Yeah.
Great.
Great question.
Ms. Cecilin, can someone there tell Brian a little bit about the globe research that you're doing or that you will be doing?
Michael, Mia, Makari, why don't you come up here? We have our 3 coming up right now.
Excellent, excellent. Thank you. And then we'll switch over to Fairbanks just to let you know and get yourselves ready to unmute. Not just yet, though.
Get up, Mia.
Ask a question.
Get up, come over here so they can see you. It's okay. Come on.
It's all right. We're all friends here.
Yes. Hello.
Are Michael, Mia, and Makari, and they have gone out for data collection every time, and I'll let them tell you a bit about what they collect. So Mia, what do you collect when we go out?
I just get the water sample.
For dissolved
oxygen test.
Wow, that's super important to do the water quality samples. That's super important. That's something you just can't really tell by looking at the water. So you have to do those. That's really important for sure.
No, I don't. I did the pH. He did the pH.
You did the pH the last few times.
Okay, I'm hearing pH. Who did the pH measurement? Okay, tell me your name again.
Michael, Makari.
Okay, thank you, Michael. Okay, so we're doing some water quality measurements, some pH measurements. Anything else?
We did the temperature too.
Okay.
Did you do the temperature of the water or the air or the surface?
The temperature of the water.
Of the water. Okay. Very cool.
Anything else?
And we don't we do that by cooking too?
It's called macroinvertebrates. We've also tried to do macroinvertebrate testing, but we haven't been able to find any.
Okay, but that's super important too. You know, doing the data and having no data found is super important as well. Because that just tells you something even more about the environment, that environment isn't suitable for the macroinvertebrates. So having no data is super important as well. Yeah.
Awesome. How often do you collect data?
Every Saturday. No.
Every Saturday?
Every Saturday.
Okay.
Wow,
Very good.
Saturday. That's impressive.
That's great. All right. Thank you very much. Anything else you need to tell us about the data measurement?
Michael wanted me to mention that we're comparing to how fish thrive, salmon.
Oh.
Very cool.
And very important for Alaska specifically to be studying the salmon and their ability to thrive. That's wonderful. Yeah. Great work. Awesome.
It's all those little parts of the ecosystem that matter, and your understanding of those is super important. That's great. Great work.
Awesome. Thank you for the work you're doing. All right, we're going to switch over to Fairbanks for some questions and to hear about what they're doing. And I know we're running right up to our time here, so I hope you can stay connected just a little longer. Is that okay, Ms. Cecilin?
Do we need to get them back to class soon? Okay, we're good.
Okay, we'll wrap it up quickly, but let me go over here. All righty, so Ms. Dilbert, let's see. Yep, Ms. Dybert, I'm sorry, my mistake. Ms. Dybert's class, if you want to ask some questions of Brian, and then we'll get into the research you're doing, or if you want to do it the other way around, whichever works for you. Go ahead.
Okay. Hi, Brian. My name is Elijah, and I am 9 years old. The question I was wondering is, how do the satellites, when there's, how do they get reception and tell you from way up there?
So yeah, so that's a great question, because a lot of the satellites that we work with are, 300, 400, 500 miles above the Earth. I mean, and then there's ones that are way out there, 1 million miles away that are out, like, looking at other planets. So they basically ping off of other satellites, and they have, these special antennas on them as well that are super high powered and able to communicate with us.
Okay.
Think of it as like a supercharged radio.
Yeah. Great analogy. Great, thank you. All right, other questions? Thank you.
What does NASA stand for?
What does NASA stand for? That's a good question. So it's National Aeronautics and Space Administration.
Say thank you.
Thank you.
You're welcome. Great questions.
Hi, I'm Kira.
Louder.
Hi, I'm Kira, and have you ever seen a satellite?
Are you saying what? Looking up into space, or are you saying like in person when it was being built? Let me answer it both ways. Yes, I've seen them while they were being built. I've been in the room while they were being built, but then I've also been in an area where it's super dark at night, and I'm able to see. You're able to sometimes see satellites flying overhead because they kind of look like an airplane, but they're moving super fast and they're super far away, and a lot of them don't have flashing lights. And then also you can see the International Space Station on really clear, dark nights as well.
Mm-hmm.
Yeah, great question.
Yeah, and you can track the International Space Station.
Mm-hmm.
There's an app on your phone you can get, and it'll tell you when it's about to be overhead, and you can go out and see that. Yes. Great answer and great question. All right, any other questions? And if not, then can you tell us about the research you're doing?
Hi, Brian.
Hello.
My name is Alden, and I was just wondering, how do you get the satellites up there?
So the satellites, if you saw that rocket launch earlier on the screen, so the rocket has all this, this fuel in it, but way at the top of it is where we put the satellite. So it's kind of like putting it in like a big tin can. So right on the nose of the rocket is where the satellite is. So once it gets into space, the rocket goes through stages, and eventually the thrusters drop off, and then the bottom portion of the rocket drops off, and it leaves just the capsule with the satellite in it, and that opens up, and then basically the satellite gets pushed out into space outside of Earth's, outside of the atmosphere. So, and then it's able to start opening up and working. So yeah, it takes a lot of effort and a lot of fuel to get it up into space on the rocket.
Thanks.
You're welcome. Good question.
Hi, Brian. My name's Isaiah, and how much fuel does it take to get it up there?
Oh, that's a good question. All depends upon the size of the satellite. So, there could be, 1 million pounds of rocket fuel in a rocket to get a big satellite up into space.
Jeez.
Because what it has to do is it has to get out of the atmosphere quickly, and it has to, start pulling away from Earth's gravitational pull as well. It's called the escape velocity. So it has to have a lot of power because it's super heavy to get it up into space. Yeah.
Thanks.
You're welcome.
Okay, do you want to tell us about the research you're doing? Or if there was another question, I didn't mean to cut that off, but I do want you to tell Brian about the research you're doing as well.
We have one more.
Okay.
Hi, I'm DJ, and I want to ask you, how do the satellite point down to the ground?
So yeah, so they have a steering system on them, where we can actually control that. We can control that from Earth. It's like a fancy remote control, and we can actually take them and turn them in the direction that we need, so that the instrument that was taking the measurements can point down to Earth, or if it needs to point to another. ICESat 2 is cool because it can do what's called off pointing. So if the satellite's normally pointing in a certain way, the people at Mission Control can turn the satellite a little bit so it's pointing in a different direction to measure something else. So yeah.
And I want to add to that, there's another Meet the Scientist that we did with scientist Marilee Roulet, I believe her name is, but it was on the SAGE 3 instrument, which is on the ISS. And they had to do some really tricky things to get that satellite to point it just the right direction. So if that's a question you'd like to know more about, you can go watch that Meet the Scientist session on SAGE 3 and learn more about how they point satellites and instruments.
Yep.
Awesome, thank you. And then we'll tell you about our project.
I was the one.
Okay.
So we were going to we were every Friday we were going outside and going to check our winter berries, which is like down there. Every Friday we used to do that, but we counted our things and like rotted
the things that are rotted and ripe and hard, damaged. And then the last time we looked, they were all gone, and we usually count how many are gone in there again.
Oh, that's very cool. Wouldn't have thought of that, but that's great.
And you're doing some work with trees also, right, Miss Divert? And some birch?
Mm-hmm. A lot of it.
Yes. But you're making really cool birch baskets with the birch bark. So
Yeah.
Oh, yeah.
very nice. All right, let me just go back and give you one go back each, and then we'll sign off for the day. Any go backs from Metlakatla? I
Bonnie, you want to go back?
Oh, I'm sorry. That must be a Bonnie Murray word. Is there anything you'd like to go back to and ask more about, or any questions that didn't get asked?
I think these guys have one more question.
Excellent, go for it.
Go ahead, Michael.
Do you guys have any proof of aliens, or have you guys ever seen an alien?
Oh.
Yeah.
Go
Nope.
ahead, Ryan.
Nope. Nope.
We don't, but I will tell you, the rover that is on Mars right now, Curiosity rover, is the first rover that is able to actually dig into the ground and ingest what it digs up. Not digest it like you digest food, but it can take it, the material inside the rover and analyze it. And we're analyzing for organic compounds, which would be signs of life. So no, we have not found the aliens yet, but we're looking on Mars with the Curiosity rover.
Yeah.
They're hiding something. Straight up no.
Can you guys thank Bonnie and Brian for their time today?
You're welcome.
Thank you both. Yes, thank you also. We both enjoyed being with you greatly. And if you have any follow-up questions, you can get them to me or to Brian. Miss Cecilin knows how to do that. And we look forward to hearing from you.
Thank you.
Bye.
Let's say goodbye to Fairbanks. Thank you so much for connecting. Thank you. Goodbye. One last goodbye, Brian.
Bye. Thank you.
All right. Thank you so much. We're going to sign off for now. Watch the recording if you want to see any of this information again.